Good. All right, let's keep going. All right, now, this is just some more terminology, this slide. You know, I did email you guys the notes, so you should have it in your inbox if you haven't looked yet. Again, this is what I said before. With an ordered pair of numbers, A, B, the first one, A, we call that the x coordinate of the point. This one here, B, that's the y coordinate of the point, okay? Now, and we also have this notion. This is actually pretty useful. 2 points are said to be equal. You know, 2 points, that is. They're equal exactly when their coordinates are the same. Their corresponding coordinates are the same. So in other words, their x coordinates are equal to each other, and their y coordinates are equal to each other. Okay. Another way of saying that visually, which is the next line, is that when you plot that 2 points are the same, they're equal, exactly when they coincide when you plot them in the Cartesian plane. In other words, they're on top of each other. That's another way of saying it. Keep in mind also, just like with the number line, remember how in the number line, every number corresponds to a unique point on the line? Same thing with the Cartesian plane. Every ordered pair of numbers corresponds to a unique point on the line, in the Cartesian plane. An implication of this is that the order matters, as you can see. That's what I'm trying to say here. Because again, they're equal only when their corresponding x and y coordinates are equal, when they have the same x coordinate and they have the same y coordinate, right? So order does matter. It's not like with a set, like a solution set, where, I don't know if I said this, but in a set, you can list the elements in any order you want. Here, order does make a difference. Okay. These are just some more examples. For instance, usually what I do is I do this with students in class as well. But let's say we wanted to plot these points, -3, 0. I mean, they're plotted already, but let me go through it anyway. So we start the origin. We're going to move to the left 3 units. In other words, we're locating -3 on the x-axis, which is over here, 3 units to the left. But since the y coordinate is 0, we're not moving up or down. We're stuck here. So -3, 0 is this point. For the next one, 2, -1, you locate 2 on the x-axis by going 2 units to the right. Then the y coordinate being -1, you're going to go down 1 unit, as you can see. Good. Here, -1, -1, right? To get to that point, to plot it, you would have to go 1 unit to the left and then go down 1 unit. Okay? That's the idea. Okay. Yeah, I know they're plotted already, but hopefully you still get the idea. So, I mean, my experience when teaching this material, this section, is that most students seem to get it immediately, maybe because they've seen it before, I don't know. But again, if you're not getting it, you know, don't be afraid to say something, but that's why there's not too much material in 2.1. All right. Now, let's get to our distance formula. So again, this is how we find the distance between 2 points in the Cartesian plane. So I said, let's let P be this point, have these coordinates. So P is this point. Q is this point. The distance between them is given by this formula. All this is saying is you subtract the x coordinates from each other. That's what this is. Square the difference. Subtract the y coordinates from each other. Square that difference. Add the squares, as so. Take the square root of that sum. That's what we're doing here. I drew P over here and Q over here. I didn't draw them, actually. I plotted them. They don't have to be in these exact positions. But what's going to happen is this. The distance is the same as the length of the line segment connecting P with endpoints P and Q. So the distance between P and Q is the same as this lines, as the length of this line segment. And how do we do that? Well, Pythagorean's theorem comes into play here. But before we get to that, let's do an example. So here, let's find the distance between points 1, 4 and 2, 7. So I put the formula here. So I'm going to let P be the first point and Q be the second point. And then we're going to use this formula. So again, what happens? Well, we subtract one x coordinate from the other, right? So we're going to subtract 2 from 1. 1 minus 2, in other words. Square that. Then same thing for the y coordinates. We have subtracting 7 from 4. Square that difference. 4 minus 7 squared. Add the squares. Oh, sorry, before that, we have negative 1 squared plus negative 3 squared. We're going to add those squares, as you can see. We get 1 plus 9, which is 10, but then we take the square root of that. Now, here, what I'm really just trying to illustrate here is that you can subtract in any order you want. Here, for instance, I did 1 minus 2. Here I did 4 minus 7, which really amounts to saying P is the first point, 1, 4, Q is 2, 7. But really, it doesn't matter, mostly because we're squaring. Right? So here, for instance, if I did 2 minus 1, so that's what I'm doing here, 2 minus 1, for this difference. Then if I did 7 minus 4, as you can see, since I'm squaring, the answer is going to be the same. Namely, we're going to have 1 squared plus 3 squared, which is 1 plus 9. Square root of that is the square root of 10. So we get the same answer. Okay? And that's good. So really, as long as you're subtracting the x coordinates from each other and the y coordinates from each other, no matter what order you subtract, you're going to get the same answer if everything else you do is right, because you're squaring. Okay, so I hope that makes sense. I just want to sketch the proof as to why this formula is true. I guess you could say it's the mathematician in me. Mostly because, when mathematicians have a fact or a theorem or, which is a proven statement, they like to prove it. Hence, I just said proven statement. But let me give an outline of a proof as to why this formula is true. It's also in the book. I just redrew P and Q just to make the sketch a little bit easier. It really doesn't matter where they are relative to the x and y axis. Okay. Now, if we have this P and Q, right, we want to somehow get the length of this line segment. That's what we want to do. I mean, between any 2 points in the plane, you can draw a straight line connecting them. I don't remember if that's something you can prove or if it's just a fact we take to be true. But for now, we know it's true. So now what we do is this. We can actually form a right triangle where PQ, that line segment here, is the hypotenuse, the longest side. That is the side opposite the 90-degree angle. Now, how do we do that? This is what I'm trying to show you with these dashed lines. You know, you have these dashed lines, as you can see. I'm not sure why that Y1 is there. I thought I got rid of that. Let me get rid of that. This also should not be here. Okay. As you can see, we have these dashed lines. Okay. And then this is drawn horizontally. Okay. And because it's horizontal, I'll get to that later. Here we draw this vertical line from Q. Now, since this line is vertical, okay, you may not see it yet, but basically any point on this line has x coordinate x sub 2. Namely, because to get to this line, to any point on the line, you have to go to the right x sub 2 units. You know, your distance, your horizontal distance to the y-axis is not changing. But basically, after drawing these dashed lines, this point here, I mean, hopefully you can see visually, has these coordinates. It's over x sub 2. It's at the same height as P, so its y coordinate has to be y1. You know, the y coordinate tells you how high you are, up or down, from the x-axis. So altogether, we get this right triangle. Now, the length of this line segment, right, that should be easy. That's just x sub 2 minus x sub 1. The length of this line segment is y2 minus y1, okay, as you can see. Okay, hopefully that's easy to see. So basically, we're going to have this right triangle. We have this length, which is x2 minus x1. Here we have y2 minus y1. Okay. Then to get the length of PQ, we just use Pythagorean's theorem, and that's what I'm doing here. I mean, again, it's only a sketch of the proof because, you know, we don't know where P and Q are relative to the x and y axis, but hopefully that gives you the idea. Okay.